Hey everyone, and welcome. Okay, let's just dive right into this. Today, we are going to unlock one of the absolute most fascinating concepts in our Class 10 math journey, and that's triangles. But listen, I don't want you to just look at this as, another boring textbook chapter. Instead, I want you to imagine we are building a detective's geometry toolkit today. We're going to decode triangles together, step by step, and really figure out the hidden rules that govern their shapes and sizes. By the end of this explainer, you are going to have complete conceptual mastery over how triangles relate to one another. So grab your mental notepad, clear away any distractions, and let's get started.
To build our toolkit, we first need to clear up a really common confusion. I have a question for you. Are all circles congruent? Think about a tiny 1 rupee coin and a massive bicycle wheel. They're both circles, right? But are they exactly the same? Well, no, obviously not, because they have totally different radii. Some circles are perfectly congruent, if they have the exact same radius, but most aren't. However, they all clearly share the same basic shape. And this brings us to a super foundational concept.
That coin and wheel brilliantly illustrate the difference between being congruent and being similar. Congruent figures are basically identical twins. They have the exact same shape and the exact same size. If you place one over the other, they cover each other perfectly. But similar figures, they're more like zooming in or out on a photo on your phone screen. The shape remains exactly the same, but the overall size changes. So, all circles are similar, all squares are similar, all equilateral triangles are similar. And today, our detective work is going to focus entirely on this idea of similarity. Here's our quick game plan for today. We're going to cover 1. What similar figures actually are. 2. The basic proportionality theorem. 3. The AA criterion. 4. The SSS and SAS criteria. And finally, a complete summary to lock it all in. Let's jump in.
Starting with our first agenda item. What exactly are similar figures? Specifically when we're dealing with polygons, like our friend the triangle.
So a triangle is just a polygon with 3 sides, right? For any 2 polygons, including triangles, to be mathematically considered similar, they absolutely have to pass 2 strict conditions. Condition 1, their corresponding angles must be perfectly equal. If this happens in triangles, we call them equiangular. Fancy word, simple concept. Condition 2, their corresponding sides must be in the exact same ratio, which means they are proportional. You can't just have one side double in size while another triples. No, they all have to scale up or down by the exact same multiplier. Keep these 2 golden rules in the back of your mind. Okay, let's step into the real core of this subject. This is where our detective work truly begins. Section 2, the basic proportionality theorem. I want you to meet our first star witness, an incredibly famous Greek mathematician named Thales, who lived way back around 600 BC. Thales noticed this really important, undeniable truth about equiangular triangles. Remember, those are triangles that have the exact same angles. He figured out that the ratio of any 2 corresponding sides in 2 equiangular triangles is always exactly the same. And to prove this, it's believed he used a foundational rule that we now call the basic proportionality theorem, or honestly, just the Thales theorem. Let's break this down completely so you can see what he saw. So what actually is this theorem? To truly master it, let's act like we're study buddies at a whiteboard and just do a quick activity right out of your textbook. Imagine drawing a simple angle. Let's call it angle XAY. We're going to construct some lines on it and watch Thales' magic happen right before our eyes. And hey, don't let the alphabet soup of letters intimidate you. It's wonderfully logical once you see it. Okay, let's take this construction step by step. Follow along with me here. Step 1. On the lower arm of our angle, let's mark 5 points that are perfectly equally spaced out. We'll name them P, Q, D, R, and B. So that little segment AP equals PQ, which equals QD, and so on. Make sense? Step 2. From that very last point, point B, we draw a straight line all the way up to intersect the top arm at a point we'll call C. Boom, we've just made a big triangle ABC. Step 3, and this is the absolutely crucial one. From point D, which is the 3rd mark we made, we draw a line perfectly parallel to that baseline BC. This new line hits the top arm at point E. Now, what's really interesting here is the ratio of the side we just split. Look at that bottom line. Point D splits the whole segment AB into 2 smaller parts, AD and DB. Since we used equally spaced marks, we can literally just count them. Segment AD covers 1, 2, 3 small parts. Segment DB covers 1, 2 small parts. Therefore, the ratio of AD divided by DB is exactly 3/2. Pretty straightforward, right? But here is where the geometry gets thrilling. What about the top arm of our angle? The parallel line split it into segments AE and EC. If you were to take a ruler right now, physically measure AE, and divide it by EC, what do you think you'd get? You would get exactly 3/2 as well. Both sides were divided into the exact same ratio. So the grand realization here is that AD over DB is mathematically identical to AE over EC. And you might be thinking, is this just a lucky coincidence? Not at all. Whether you used 5 segments, 10 segments, whether you drew your angle super wide or really narrow, as long as that inner line DE is strictly parallel to the base BC, this proportional magic will always happen. And that brings us to the formal definition of Theorem 6.1, the basic proportionality theorem. Listen closely to this, because it's huge. It states, if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. I highly encourage you to lock this into your memory. It is the most powerful tool in your entire geometry toolkit. Whenever you see a line drawn parallel to a base inside a triangle, you immediately know those sides are sliced into equal proportions. And remember, the reverse is totally true too. If a line divides two sides in the same ratio, it simply must be parallel to the third side. All right, moving right along to section 3. Let's use our freshly learned BPT tool to unlock our first major shortcut for proving triangles are similar, the AA similarity criterion. Remember those two rules for similarity from earlier? Equal angles and proportional sides. But let's be honest, checking all of those every single time takes forever. Theorem 6.3 is our first shortcut. It says that if in two triangles the corresponding angles are equal, then their sides are automatically proportional, and hence the triangles are similar. Let's prove it visually. Imagine we take a small triangle ABC and a larger triangle DEF. We already know angle A equals angle D, angle B equals angle E, and angle C equals angle F. Now we use a clever little construction trick. We basically measure a piece off the big triangle's side, marking point P so that DP is the exact same length as AB. We do the same on the other side, marking Q so that DQ equals AC. Then we just draw a line joining P and Q. Because we constructed it this specific way, that small triangle ABC is completely perfectly congruent to this new upper triangle DPQ. Since they are identical twins, angle P must equal angle B. But wait, we already knew angle B equals angle E, so logic tells us angle P equals angle E. You with me? Because these are corresponding angles, it means the line PQ is absolutely parallel to the base EF. And what did we just learn happens when a line is parallel to a base? The basic proportionality theorem. So by BPT, DP over PE absolutely must equal DQ over QF. Following that logic all the way through, and remembering that DP was just a stand-in for AB, we can conclude that the ratio of AB over DE equals BC over EF, which equals AC over DF. Think about what we just did. We started with only equal angles, angle, and mathematically proved that the sides scale up perfectly in the same proportion. The beautiful takeaway here? You don't need to measure the sides if you know all three angles are equal. In fact, because of the angle sum property of triangles, if just two angles of one triangle match two angles of another, that third one has to match too, right? So you can use the even faster AA similarity criterion. We are cruising now. Let's hit section 4 and pack the final two massive tools into our geometry toolkit, the SSS and SAS criteria. SSS stands for side, side, side. This is Theorem 6.4, and honestly, you can just think of it as the exact reverse of the AA criterion we just proved. The SSS similarity criterion states that if the corresponding sides of two triangles are proportional, meaning they all share the exact same scaling ratio, then their corresponding angles are guaranteed to be equal and the triangles are similar. So if you're playing geometry detective and you measure the sides and see they all perfectly double in size in the larger triangle, you can confidently declare, without ever picking up a protractor, that all the angles are perfectly equal. Next up is Theorem 6.5, the SAS, or side angle side criterion. This one is like a really powerful hybrid tool. What if you only know one angle is equal? The SAS criterion says that if one angle of a triangle is equal to one angle of another triangle, and the two sides that include or sort of wrap around those equal angles are proportional in the same ratio, then, boom, the triangles are similar. If you do an activity measuring triangles this way, every single time, that third side will scale perfectly, and the other two angles will naturally match up. It's a fantastic time-saving shortcut.
Fantastic work, seriously. We've covered a lot of deep conceptual ground today. Let's transition to our final section and review this master toolkit we've built together.
Here is your ultimate summary. I want you to take a mental screenshot of this. When you need to prove two triangles are similar, look for these clues. First, AA or AA. If the corresponding angles are equal, they are similar. Second, SSS. If all corresponding sides share the exact same ratio, they are similar. Third, SAS. If one included angle is equal and its wrapping sides are proportional, similar again. And overarching all of this is our big one, the basic proportionality theorem. If a line cuts through parallel to a side, it divides the other sides in the same ratio. Just remember, all those complex textbook proofs we talked about, they are really just logical stepping stones to guarantee these simple, elegant rules are always true for you. Your textbook also notes some advanced tools like RHS, right angle hypotenuse side similarity, and ratios of areas, which build directly on these exact foundations.
And that brings me to a final, slightly provocative thought to leave you with as you head into your own practice exercises. What do you think happens to these similar triangles if you take a right-angle triangle and drop a perpendicular line straight down from the 90-degree vertex directly onto the hypotenuse? Does it create total geometric chaos, or does it spawn perfect, mathematically similar miniature triangles inside? I'll let you explore that beautifully structured mystery on your own. Thank you so much for joining me on The Explainer today, and keep enjoying the brilliant logic of math.